Not true. 0.
Except for 0.
Infinity.
Infinity divided by infinity is infinity.
No, infinity divided by infinity could be 7. Infinity divided by infinity could be 13. Could be negative 9. Could be pi. Could be infinity. Could be 1. Could be 0.
Can't be 0.
Could be.
No.
Infinity divided by infinity could be 0.
Give me an example where infinity divided by infinity is 0.
The limit as x approaches infinity of x squared over e to the x. As x approaches infinity, what does x squared approach?
Infinity.
Infinity. What does e to the x approach?
Infinity.
So that's an infinity over infinity. But guess what the limit of their quotient approaches? 0.
That doesn't count. Not using. It doesn't count.
If the bottom infinity is a massively larger infinity than the top, then yeah, it's 0.
It's not 0.
It is 0.
No.
The infinity that this approaches, as compared to the infinity this approaches, because the bottom approaches infinity so insanely faster than the top, that fraction approaches 0.
But it doesn't hit 0 ever.
Well, you never hit infinity, so how can you divide infinity by infinity?
You can't. You never hit 0. Without having 0 on the top, you cannot get 0. And 0 is not infinity.
Mathematica would say 0 for this. No, I mean, it's a little bit cheating doing a limit. I get you. For the same, if you use a limit, guess what 0 divided by 0 is? 3, negative 5, 7, infinity, 0. The actual number 0 divided by 0 is undefined. But if you have quantities that are both approaching 0, top and bottom, their fraction, their quotient could approach anything. Like holes, right? Holes in graphs. That's a 0 over 0, but the limit approaches 5. Okay. All right, let's do some proofs. Let's look at this first page of this packet you just got. Okay?
Let's just do all these problems.
And let's just start going through them. Let's do 5 first. Number 5. First of all, before we do number 5, let's talk about what it is we are trying to do here with these proofs. So let's start with one that's a little bit easier. Let's prove that 3 plus 2 is equal to 4 plus 1. Okay? And there's a little bit of debate amongst math teachers as to what it is we are actually trying to do here. I come from very much a logic slash, what did you say? Did you say farm? I never lived on a farm. I lived next to a farm. It was weird growing up in farm country, feeling like an urban person. It was so weird. I never felt country. I never felt like I just always felt out of place. Hated it. So that smell is nice. Driving that fresh country air. It's also known as manure. I'm telling you, you may sound gross, but like when I drive back to Minerva, like this time of year, or in the spring, and you smell that fresh laid manure on those fields, it smells good. It really does. It's a positive association. So I just have this nice association with it. Anyway.
It's more of fresh air from
the lack of smog?
Yeah.
That could be. That could be. All right. So what is it we're trying to prove? My background tends to be in computers and logic. And so to me, we're just trying to prove this is a true statement. And so therefore, it would be totally valid for me to use nothing but the rules of addition, simplify the left side down to 5, simplify the right side down to 5, and then obviously that is a true statement. So because this is a true statement, so is this. Okay, that's my argument as a teacher. So we've had a lot of discussions, and I do understand where other teachers are coming from, because lots of other teachers, and this is the convention your textbooks use, and if you go online and look up trig identities, they do the same thing. That is not an okay way of proving this is a true statement. Simplifying both sides down so you get this equal statement. One thing you should never do is move stuff to the other side and say, well, this becomes 3 equals 4 minus 1, and that's 3. Never, ever move stuff from one side to the other, especially if it's multiplying or dividing by a variable that can change the equation entirely. Okay? Many mathematicians interpret this very literally from left to right. You are to prove that 3 plus 2, that is the focus. Prove that 3 plus 2 is actually the same thing as 4 plus 1. And so you can't touch 4 plus 1. You can't call it 5. It's got to remain 4 plus 1 the whole time. So you have to use all of your valid math rules to turn 3 plus 2 into 4 plus 1. You work on one side of the equation. Because there's no doubt about it. If you can turn one side of the equation into the other side, clearly they are equivalent statements. So how would you do a problem like this? I'd probably say, because of our rule of addition, I can rewrite 3 as 1 plus 2. Now, technically, according to PEMDAS, which of these additions do I have to do first? The left one. But am I allowed to do the right one first?
Yeah.
Yes. Why? What property? Not the commutative property. The associative property tells me I can actually do that second. The commutative property is all about switching the orders of the numbers. Associative property is all about changing the order of the operations.
That's what I was thinking.
Well, yeah, maybe that's the more obvious, but this one's more fun. No, yeah, you totally could have. There's not one correct answer to this. Right, you're right. I have to actually use two properties this way because I use the associative property to let me rewrite it like this, and then I have to use what property to rewrite it like this. That's the commutative property. So I actually had to use the associative property and commutative property because I first rewrote 3 as 1 plus 2. Had you rewritten 2 as 1 plus 1, you then add the 3 and the 1, which is correct PEMDAS anyway, and you're done. So you're right, yeah. I purposely did it the harder way because I wanted to test your knowledge of the associative property.
Why can they say mathematicians are so lazy that then they want all these steps for proof when it's simply 5 equals 5?
Well, I'm picking a stupid example, clearly. I mean, that is not going to be a question on tomorrow's quiz.
Why not?
Prove to 3 plus 2 equals 4 plus 1. No. But this was me explaining why we take one side of the equation and we manipulate just that one side and turn it into the other side. Okay. A simple one like that. How many of you would have, especially if this was 2 column, you had to explain, not many, so far today, nobody said associative. I've heard commutative first for this one, why we can do that addition first all day today.
Well, if we broke this up to 1 to 1, all the
No, yeah, you're right. You're right. The bonus problem would be I already have the proof laid out, you just have to give the reasons for each step.
See, I can do that.
Can't you do everything? Okay, let's do number 5. Let's prove that tangent of some angle alpha plus the cotangent of the same angle is actually equivalent to the secant of that angle times the cosecant of that same angle. Those are alphas. It's the Greek letter alpha. Right. Helium nuclei? That is the notation. Yeah, I don't care what you write. It's like 3/4 of infinity. Which is still infinity. Right? 3/4 times infinity? Still infinity. Alright. So I'm going to simplify the left side because to me that's probably, I don't know, maybe a little bit easier. Now, here's the approach you're going to want to take to these. 1, you got to have your identities all memorized. 6 reciprocal identities, 2 quotient identities, 3 Pythagorean identities. But you also have to be able to identify all the possible algebraic rearrangements of those Pythagorean identities. And really, there's lots of Pythagorean identities. Okay? What you want to do is you want to look at it and it's almost like you start to do the problem in your head. I mean, it really is. Some problems have more obvious things you're going to do to them than others. I actually think this one is very much a not very obvious problem to begin with. but you almost want to try and do as many steps as you can in your head. There are going to be certain things you start to notice, and it's going to make you say, ooh, you know what, I'm going to do a quotient identity here and a quotient identity here. Get a common denominator, add those fractions together, and you'll start to notice things. So start doing steps in your head. Right now you can probably only see this problem like one step ahead. You know, maybe see this as a sine over cosine, this as a cosine over sine. Eventually you'll be able to then, okay, what would those fractions look like if we got a common denominator, added them together? Oh, that numerator is a Pythagorean identity, let's plug a 1 in, and eventually you'll be able to do steps ahead. And the reason that's important is because that's how you develop a plan as to what you're going to do. And sometimes the plan, you look at a problem and the identity starts substituting in before your eyes, and you see this thing changing, and you develop a plan, and you start doing it, and it gets you nowhere. You end up scrapping that plan, erasing all your work, and starting over again. And that happens sometimes. Okay? A good strategy, if you can't figure out a plan right off the bat, try rewriting everything in terms of sine and cosine. If you see a secant, call it 1 over cosine. If you see a tangent, call it sine over cosine. Usually, if you rewrite everything in terms of sine and cosine, you can see a pattern. You can see what you want to do. But sometimes that's not the best idea. And so, highly recommend, like, look at it for a while. Try to get steps ahead so you can kind of see what your plan is going to be. So my plan is going to be rewrite the left side in terms of sine and cosine, then get a common denominator and add the fractions together. And that's all the farther ahead I kind of saw. I don't really know where it's going to go from there. So I'm going to rewrite tangent alpha as sine alpha over cosine alpha. Cotangent becomes cosine alpha over sine alpha. And then again, we're not allowed, or we're not going to do anything to the right side. All right, so I've got two fractions with obviously different denominators. Hello. All right.
Oh, I see what you did there.
Yeah, because it's obvious.
Yeah.
Okay. So we need a common denominator. What's the common denominator going to be for these two fractions? Happen? If you're adding two fractions together of which the denominators have nothing in common, what do? You just multiply them together. The common denominator is going to be sine alpha cosine alpha. It's the product of the two. So we're going to multiply top and bottom of this fraction by sine alpha. We're going to multiply top and bottom of this fraction by cosine alpha. So we get sine times itself, so that's a sine squared over the common denominator. The second numerator becomes cosine squared over the common denominator. All right, so now we've got two fractions with the same denominator. Let's combine them as a single fraction. So the numerator is now sine squared alpha plus cosine squared alpha over the common denominator, sine alpha cosine alpha. And again, the right side has not been touched. At this point, some of you should be able to look at that and say, ah, and I see it. And you kind of see what the rest of the steps are going to be for the rest of the problem. No, that's fine. It's our first one. What is sine squared alpha plus cosine squared alpha? It's 1. So we now have 1 over sine alpha cosine alpha. Can I split that fraction up into 1 over cosine alpha times 1 over sine alpha? By the rule of multiplying fractions? Right? And what is 1 over cosine? So that becomes secant alpha. And what is 1 over sine? And that's it. We're done. Okay? This is kind of a common idea. whenever you have two fractions, one with sine, one with cosine, get a common denominator, multiply them together, you might get a Pythagorean identity that shows up. Okay? I bet there's a way we could have done it, but leaving it as tangent cotangent, but getting the 1 plus tangent squared identity. I bet you. Okay. Any questions on that one? Pretty cool, right? All right, let's do the next one. I think the next one has a little bit more obvious initial steps. Yeah, maybe not. Prove cotangent squared A equals cosine squared A plus the quantity cotangent A times cosine A squared. Okay, so again, I like to take a little time, look at it, try and see the first few steps in our head. So here's what I notice as I look at this. If I distribute this exponent over this multiplication, are we allowed to distribute exponents over multiplication? I'll end up with two terms on the right side. So clearly I'm going to be manipulating the right side, not touching the left at all. If I do that, I'm going to have two terms on the left. One of the terms is cosine squared. The second term is going to be a cotangent squared times a cosine squared. Both terms will have a cosine squared A in them, won't they? So I'm going to factor it out. If I factor a cosine squared out of both of these terms, what I'm going to be left within the parentheses is a 1 plus cotangent squared, of which a light bulb goes off in my head, because that's what Pythagorean it is. Right? So that's my plan. That's what I want to do. So let's do it. Okay. So the first thing I do is distribute that exponent over the multiplication. I get cotangent squared A times cosine squared A. The second step is to factor out a cosine squared A. So I'm going to be left with 1 plus cotangent squared A. And I'm going to stop there and let you stare at that for a while because a lot of people have been a little bit confused on that step today. Does that make sense, or? Right? It's no different than having 2 plus x times 2. And I'm factoring the 2 out, and I'm left with 1 plus x. Right? It's the same idea. Instead of 2, I have a cosine squared A. Instead of an x, I have a cotangent squared A. Okay? So now, inside the parentheses, we have 1 plus cotangent squared A. We have memorized 1 plus cotangent squared is cosecant squared, the Pythagorean identity. So this becomes cosine squared times cosecant squared. 1 plus cotangent squared is cosecant squared. 1 plus tangent squared is secant squared. Sine squared plus cosine squared equals 1. Those are your three Pythagorean identities. So now I use a reciprocal identity. Cosine squared A times 1 over sine squared A. So if I use my rule for multiplying fractions, that becomes cosine squared A over sine squared A. And what is cosine over sine? So you get cotangent squared equals cotangent squared. Okay? Yes, because it's technically using our exponent rules. But, you know, technically this right here is the same thing as saying cosine A over sine A, then squared, like that. So then you don't have to show that step or break that down there. It's the same idea as if you're ever dividing like 8 to the third divided by 4 to the third. Whenever you're dividing powers that have the same exponent, you just divide the base. This becomes 2 to the third. So it's the same idea. Cosine squared, sine squared, they both have the same exponent, so you just divide the bases, so you just get cosine over sine.
How many cases cool it, pay attention. You're going to need to.
A lot. Like 3. But we're just beginning this. We're going to spend a lot of time on this. So either we spend a lot of time on this so that we get better, or we spend a lot of time on this, so that's a lot of time missing lots of points. That's supposed to be funny. Nobody laughed. You'll get the hang of it. Like, for example, turn the page. I'm going to have a problem on there tomorrow, like number 8. Number 8, you should all, a lot of you should be able to nail right now pretty easily. Do it. Do number 8. Work on the left side. Rewrite everything in terms of sine and cosine. And then use your fraction rules to just cancel and simplify that fraction down. See what happens. Number 8. Do you know your reciprocal identity? Do you know your quotient identity? So then now you won't. What's your trig identity's cheat sheet up?
I'm not getting that hour one on that. No.
Please excuse this interruption for one afternoon announcement. Attention, early release National Honor Society seniors. Please report to the library reference room to staple Santa phone letters today. Again, early release National Honor Society seniors. Please report to the library after class and report to the reference room to staple Santa phone letters. Thank you.
Okay. So cotangent becomes cosine A over sine A. All right, you should know that. Cotangent's x-coordinate over y-coordinate. We've known that for weeks. Secant is 1 over cosine. We also should already know that because it's the reciprocal of cosine. So when you multiply these fractions together, you get cosine A over sine cosine. So the cosines cancel, so the left side becomes 1 over sine. And we know that 1 over sine is cosecant. That's it.
You have to show that's like...
You could I would expect a lot of students to just do that.
Okay, yeah.
Yep, absolutely. How are we doing time-wise? Time to do another one? 7 is somewhat similar to 6. You're going to want to work on the right side. First step, factor out a cosine squared. First step, factor out a cosine squared.
Where do you do that?
And that's basically it. That's the hardest step to number 7. Huh? There will be one like that. Yeah. Yeah, they won't be crazy. We'll spend a lot of time before the quiz tomorrow going over these. 4 times the amount of time it takes me? I don't know. I haven't done it yet.